Hello, my name is Ali Rahman and this is my MSc Computer Science dissertation demo. My project is titled Edge AI for Patient Safety Monitoring in Hospital Rooms, a YOLO version 8 nano based evaluation of accuracy, latency, and privacy trade off. In this video, I will walk you through the problem I was solving, my solution, a live demo of the system, the key part of the code, my result, and my conclusion. Let's get started. The problem I am addressing has three parts. First, hospital cannot continuously watch every patient room. Falls are the one of the most common and most harmful inpatient incident worldwide, according to WHO. Second, when a fall does happen, delayed recognition make things worse. If a patient suffer a head injury and nobody notice for several minutes, the clinical outcome can significantly worse. Existing solutions that use cloud-based video analytics introduce network delays and move sensitive patient video outside the hospital environment, which create both a latency problem and a serious privacy governance problem. So the question my dissertation answer is, can we build a system that is fast enough, accurate enough, and private enough, all at the same time running entirely on local edge hardware? My aim was to design and evaluate a lightweight edge AI monitoring pipeline using YOLO version 8 Nano that balances detection performance, latency, and patient privacy. I had five specific objectives: design and implement a prototype edge AI pipeline for fall related event recognition, evaluate detection performance using precision, recall, F1 score, and related matrices. Measure inference latency frames per second to assess real-time feasibility. 4. Examine the privacy by design implications of local processing versus cloud processing. 5. Analyzing the accuracy, latency, and privacy trade-offs to identify the best deployment configuration. I am pleased to say that all five objectives were achieved within this project. My solution is, is a six-step video processing pipeline. Step 1. A video clip is uploaded to the system. Step 2. 10 frames are sampled evenly across the clip. We do not process every single frame, which keeps inference fast. Step 3. YOLO runs on each sample frame and detects the person in the scene. In step 4, features are extracted from each frame. These include things like, is the body lying flat? Is the person near the bottom of the frame? Has the bounding box become wide for the pose model? We also extract the position of 17 body key points. In step 5, these features are averaged across all 10 frames into clip level ratios. The standard deviation across frame is especially important. A high standard deviation means the person position change abruptly, which is strong false signal. A lightweight logistic regression classifier uses these ratios to predict fall, no fall. The decision threshold was tuned on a validation of subject to 0.15. I compared three model variants: standard RGB, blurred RGB for privacy, and YOLOv8 pose using body key point. Let me now show you the system running in live. Now let us first upload a video in which a person is lying on the bed. As you can see, he's doing nothing. So you can see there is no fall detection. Current prediction, no fall detection. There, these are the sample frames, and this is a post skeleton output, and you can see there is no fall in our graph. You can see it is below the threshold, and it has a privacy score of 4 because you cannot see anything here, just a skeleton. Now if I switch my version to blurred, you can see now the video is totally blurred. You cannot see the person. This has a privacy score of 3. Now let us switch to RGB. Now this does not apply any filter, and you can see still no fall, and the privacy score is 1 because there is no filter or anything. There is no privacy at all. Now let us upload a video in which there is a fall. Now see, a person is sitting in the chair and he suddenly falls. Now if I switch my output to this and run it, you can see it detected the fall. Here you can see the fall probability 0.59. This is the sample video, and you can see it from here. The graph rises, and if you can see the the model used is version 8 pose. Now if I upload another video of a fall on a bed, now if a person is on a bed and he falls on the bed, now you can see the system clearly predict that the fall. These are the sample video. So this is my code. Now let me show you my notebook. This is a Google Colab notebook. In this you can see subject 1 and 2. In this you can see subject 1 2 are used in training, subject 3 is used for validation, and subject 4 is used for testing. This prevents subject leakage. If clip from the same person appear in both training and test, the model could memorize the appearance rather than learning general fall patterns. This is the whole code in Jupyter. These are the samples. If you go down, now this is the code that we run in our I named it interface. In my notebook it is named app. I renamed it to interface. That is the file I run, and it is using a Gradio interface that I just showed you on the web. Now get back to presentation. Here are the quantitative result from the evaluation. Look at F1 score bar on the chart left. You can clearly see the progression RGB of at 0.67, blurred at 0.722, and pose at 0.842. The metrics that matter most for patient safety recall is the ability to detect actual fall. The pose model achieved 0.9412 recall, meaning 94% of fall were detected. Interestingly, the blurred model outperformed the standard RGB, which suggests that privacy-oriented processing did not hurt performance. In fact, rendering visual noise may help the model focus on relevant motion patterns. The Pose model also achieved the highest ROC and AUC of 0.938, showing strong separation between fall and ADL classes across all decision thresholds. And importantly, on latency, the Pose model was actually the fastest at 39.27 millisecond per frame compared to 64 millisecond for both RGB variants, so the most accurate model is also the fastest. This directly answers our research question. Accuracy, privacy, and latency are not necessarily in conflict. Let me walk through the visual evidence. Top left, the ROC curve for all three models. The green line for the Pose model sits clearly above the other two with an AUC of 0.938. The closer ROC curve at top left corner hugs at top left corner, the better the model ability to separate fall from non-fall. The top right, the cluster bar comparing precision recall and F1 across all three models. Notice that for the Pose model shown in the rightmost group, the recall bar, which represent detect fall, is significantly taller for RGB or blurred. The bottom section shows the confusion matrix for all three models on the test set. 37 clips from the subject 4, 17 which were false and 20 were ADL. For RGB model, 6 falls were missed, that is Fn equals 6. For blurred, 4 falls were missed, but for Pose model, only 1 fall was missed out of 17. That single fall negative is what derives the highest recall score. And finally, at the bottom, the latency comparison confirmed the Pose model runs at 39 milliseconds, giving approximately 25 frames per second, sufficient for near real-time monitoring on local hardware. I want to be transparent about what this project does not claim. The dataset used GMDCSA24 is a home-like indoor dataset, not real hospital footage. So the result represent technical feasibility, not clinical validation. The dataset has only 4 subjects with one held out for testing. This limits how confidentially we generalize to wider patient population. The system does not model time explicitly. It cannot pinpoint the exact second a fall happened. For that, we would need a LSTM or sliding window approach across continuous frame. Latency was benchmarked on a local CPU, not a real Jetson or NPU edge device. So actual VOD device performance would need separate testing, and the system was not tested on continuous live streams. So false alarm rates over long periods are unknown. To conclude, this project delivers a credible feasibility demonstration that lightweight, privacy-aware edge AI can support all monitoring without sacrificing accuracy or real-time responsiveness. The YOLO Pose model achieved the best performance on every metric: accuracy of 83.8, recall of 94.1, and F1 of 84.2, and the fastest latency at 39 milliseconds. Most importantly, it only missed one fall out of 17 on test. The skeleton only output proves that privacy and monitoring utility are not opposed. You can reduce identifiable imagery to body key point and still achieve strong detection. All 5 research objectives were achieved within the bounds of this feasibility study. For future, the priority would be testing on a real hospital dataset, adding LSTM based temporal modeling to detect the precise movement of a fall, benchmarking on a real real hardware, and building a ward-facing dashboard that connects model outputs to staff escalating workflows. Thank you for watching. I look forward to the QA session.